Hello, this video covers AP Chemistry, Chapter 1, which is about matter. So we have the three states of matter here. There's also a plasma state where the electrons have been ripped off the atoms and they're a much higher energy. And that's mostly found in the sun. But here in our lab, we will have solids, liquids, and gases. And there's a link below to the PhET simulation where you can heat up the molecules and cool them down and change the phase of various substances from water to helium and argon. Okay, so you can see in the solid state, you have the molecules in a fixed position. If you look at the simulation, you'll see that they are moving, but they can only vibrate. Okay, so that's the only motion that a solid can have. It's fixed in its position like a chain link fence. Okay, and then we go up to liquid. In a liquid, the molecules are touching like a solid, but they're able to rotate or spin and translate, which means go across or up and down. Excuse me. And they are still touching because they are held together, in this case, since it's water, by the hydrogen bonds in between the little molecules. If it were argon, then they would be held together by a much weaker intermolecular force that we'll cover in Chapter 11. Okay, and lastly, we have gases, the highest energy state of matter, where they are very far apart, much farther apart than this little picture shows, and they are moving incredibly quickly, bouncing all around whatever container they're in. Okay, and you'll notice that these are going to fill up the entire space of the container, so they take the shape of the container that you put them in. If you put them in a flask, they'll be flask-shaped. If you put them in a balloon, they'll be balloon-shaped. Okay, so gases take the shape of their container, as do liquids. Solids, if you put a solid in a flask, it's going to stay in whatever shape it started at. Okay, so solids do not take up the shape of their container. That one is cubic, so if you put it in or on a plate, let's say, water would spread out to take the shape of the plate, but the solid is just going to stay in its shape on top of the plate. Okay, and solids can have two forms. A crystalline solid has a definite order to it, and ice is a crystalline solid. And then you have amorphous, which means without shape. So glass is amorphous. It does not have a definite order. And that's why when glass breaks, it breaks in all kinds of random shapes. All right, here we have a flow chart that's going to show us. Let me get rid of the camera real quick. Okay, so here we have a flow chart that's going to show us the components of matter. So we have matter being anything that is made up of particles that have mass and take up space, which is volume. Okay, and that matter can be broken down into two categories. We have pure substances that are made of only one type of particle. So you have pure gold here. We could have pure water. They're made of one specific particle. Okay, that can be a compound or an atom. And then we have mixtures where we have two or more substances that have been mixed together. Okay, so a pure substance is either going to be one of two things: an element found on the periodic table, right there behind me. So if it's found on there, if it's carbon or hydrogen or oxygen or gold or copper, anything on the periodic table is going to be an element. It can't be broken down into anything simpler. And so they're made of only one type of atom. They're a pure substance. And then we have compounds like sodium chloride and H2O water, which are different elements combined, hydrogen and oxygen in this example, but they are chemically combined. So if you had pure water, it would look like our last slide where it's just one type of molecule. Okay, so we have red and white atoms in there, but they are bonded together, so it's the same component of every single molecule, okay? And then over here, mixtures. Since things are mixed together, you can separate them into two categories. We have heterogeneous, where it's a mixture of things that looks different in different parts. And then we have homogeneous, where it's the same throughout. So our examples down here are Italian dressing, where we have oil and vinegar that do not mix very well. They want to separate out. So at the top, you'll have a higher concentration of oil droplets, and at the bottom, you'll have less oil and more vinegar. And then you have little bits and pieces of the spices that are in there as well, making it different in different areas. So the bottom and the top are not going to look the same. And if we were able to zoom in to the molecular level, we would see that the molecules are in clumps as well. So you'd have a big group of oil molecules, and then you would have all of the water and the vinegar molecules separate from that. So it's different in different parts. Kool-Aid, on the other hand, is a homogeneous mixture, which is another way of saying a solution. So Kool-Aid is a solution where you have water and food coloring and a lot of sugar all mixed together. But if we zoomed into the molecules in that Kool-Aid, we would see an even distribution. So this area would look like this area, and any other area would look the same. You have water molecules with sugar spread evenly, and the food dye and whatever else is in there mixed together would be spread equally or uniformly. All right, section 4 of chapter 1 is about physical and chemical properties and changes. So a physical property is something that we can observe without changing the identity of the substance. It includes things like color, mass, and texture. If I'm talking about my coffee cup, the color of it, the shape of it, the texture of it, those are all physical properties that we can observe without changing what it is. Chemical properties you cannot observe without changing it. So if I wanted to see the flammability of this, I would have to try to burn it, and then it would change into something different. Okay, a better example would be paper. So if I wanted to know how flammable paper was, I would have to take the cellulose that's in here, and I would have to add energy to burn it, and the atoms would all rearrange and it would turn to ash, which is mostly carbon. So it goes from cellulose, which is carbon, hydrogen, and oxygen, all arranged a certain way, to mostly carbon, which is that black color that you get, and the carbon dioxide and the water leave, leaving mostly carbon behind. Okay, so I've completely changed what it is to a new substance. That is a chemical property. You can't observe that chemical property without changing the substance into something new. A physical change changes that physical property, like we said. And there are a lot of really good examples that show the molecular level in your textbook on page 11. So go to your textbook for more examples of those. Okay, so a mixture can be separated by physical means, and here's a very specific physical means. This is called chromatography. A lot of you guys have seen this in bio, AP Bio or biotech. You have a solvent down here, and this one looks like they put a dye near the bottom, and the solvent will go up the chromatography paper and separate the dyes based on their polarity usually, into its various components. So that is a physical process. You had a mixture of colors and you're separating them out. Okay. Another way would be if you had salt water and you wanted to separate the salt from the water, you could boil the water away, and any kind of change of state, boiling, melting, sublimation, condensation, freezing, all of those are physical changes because they don't change what the element or the compound is. They're just changing the arrangement of those little atoms to let them move faster, right? So those are all physical changes. So if I had my salt water, I could boil the water away. I still have water, just as steam now, and I would have salt left behind. So I'm separating that mixture by its physical properties, okay, of boiling. And a compound, on the other hand, can only be separated by chemical means. So over here, we have a nice picture of the electrolysis of water. We have a voltage source like a battery, two electrodes, the anode and the cathode, are inserted into the water, and the electricity, which is electrons moving, is able to break apart those water molecules. So the red with the two white, the electricity is going to be able to remove the hydrogens, and they will bubble away, and the oxygens will also bubble away. So you're breaking the water down, you're breaking the bonds, taking that compound, separating it. You can only do that by chemical means. All right, section 5 of chapter 1 is about work and energy. Work is the ability to apply a force over a distance. So in chemistry, an example of work would be gas's ability to push a piston up if you had it in a container. So we have a container with gas, and the gas molecules are all bouncing around. They're going to be able to hit that piston and push it up. So it's a force of them colliding with that piston, and it's going to be the distance that it raises or lowers. If we were to cool the gas down, the lid might go down. So the distance would be the change in the height of that piston. Energy is the ability to do work. So the molecules have energy, and that's why they can cause that piston to rise or fall. Energy in chemistry is mostly focused on these two things down here. So we can break down energy into two different types: kinetic energy, which is the energy of motion, and potential energy, which is the energy as it relates to position of something. So in your 8th grade science class, you might have learned potential energy and roller coasters. At the top, it has a high potential energy because of its position, okay, and it has a low kinetic energy. As it goes down, you're converting that potential energy to kinetic energy. So the potential energy would go down, and the kinetic energy, it speeds up. So the movement goes up. Okay, so these two things, energy can't be created or destroyed. It can only be transferred or transformed, I should say, from one to the other. Underneath kinetic energy is thermal energy in here. So when we take the temperature of things, we have a reaction and we feel the flask heating up. That's thermal energy being released into the surroundings of that flask. And it's causing the molecules to move faster, which is kinetic energy. Okay, over here, chemical energy is the bonds. We're talking about protons and neutrons and electrons and the atoms interacting with each other. That's what the potential energy has to do with chemistry. Excuse me. So we know that opposite things attract. If I have a positive and a negative, they're going to attract each other. The position of those positive and negative things determines its potential energy. So if I have positive and negative and they're apart, there is a high potential energy. When are these things stable? They're stable when they're together. Okay, so they attract each other. If it was the opposite of that, if I had a negative and a negative, they're going to repel each other. When are they the most stable? When they're far apart. That's the lowest potential energy if you have the same charge. Okay, so this really has to do with something called Coulomb's law, which is going to be your best friend later in the year. You'll learn all about Coulomb's law. But for now, you just need to know potential energy is related to the position of, in this case, particles. Okay, and that's chemical energy. All right, so this is just a diagram showing you potential energy. It calls it interaction energy, but this is the potential energy increasing as you go up on the y-axis. And on the x-axis, you have the distance between the two nuclei that it's showing here. Okay, so the distance between these two things. And if we look on the left over here, the force, they are attracted to each other. You guys see there's not a good spot for me. Let me make this smaller. Okay, so the force here is pulling these two things together. And if this were a marble and this were a little hill, you would let go of the marble, it would roll down the hill and it would go back and forth, right, until it settled where? Right here. It's the same thing with these little molecules. They are going to expand and contract until they find that happy place of the lowest potential energy down here in this minimum. Okay, so they are going to adjust themselves to be lowest energy possible, and we equate the lowest energy point to being stable. So the most stable things have the lowest potential energy. Okay, right here, this is the perfect arrangement that we were talking about. So this distance is going to be the radius between these two things. This is going to be the, I should say, bond length, sorry. So the bond length between these is A. Right here, you can see that it's actually going up on the other side. So what's happening here is the potential energy skyrockets right here. It goes way up. And why is it going up? Because as we get closer and closer together, you cannot have them right here. Okay, this will never cross this line. You can't have zero distance between the two nuclei because they're protons, and they repel each other so greatly that this energy skyrockets. It goes way up. So when they get too close, okay, when they're apart, they're at higher energy, like on the right. As they get closer, the energy goes down. There's a happy point where they're overlapping perfectly, and too close means that the protons are too close together and they're going to actually repel each other. Okay, and we would have an explosion there. Okay, so this is potential energy versus the distance between these two nuclei. Okay, too far apart, too close together, just right. Lowest energy, so this is stable.